this example, we have a pulley. This is a spring of spring constant K, and we have now just fixed it. We have not released it. As a result, now the spring has its natural length. There is no extension of the spring. Pulley has a mass m, radius r, I about c, that is moment of inertia of this pulley passing through its center of mass, and perpendicular to its plane is IC. Now second is we talk about the mean position of this when the pulley is in equilibrium. That is, it has been gradually being lowered, and over here it goes from here to here, and over here it achieves its equilibrium position. It has gone x units below this level. So when it goes by x units below this level, so there is an extra requirement of string, x units over here and x units over here. The string is inextensible, but obviously there has to be string over here when it goes down. To compensate for this extra requirement of 2x, it stretches itself. So when the stretch in the spring is 2x units, so obviously the tension over here is k into 2x, k into 2x is over here. If we draw the force diagram for this, k into 2x is here, k into 2x is over here, mg is here. Because this is, we are talking about the equilibrium position, so that's why we can say that is 2kx plus 2kx is equal to mg, that is 4kx is equal to mg. This is equilibrium position. We consider an instant where it has gone further below its mean position at a distance y, and it has some velocity. So from here to here is not amplitude. So amplitude is going to be bigger than y. So this is, right now, this pulley is between the mean position and the amplitude, and it has some velocity also, and obviously it has kinetic energy and potential energy. If it goes from here to here at distance y, it further goes at distance y, so there is a further stretch in the spring, that is 2y. So at this instant, it has a velocity v. Spring has extended, the total extension of the spring is 2x plus 2y, and this mass, this pulley, it has gone from this level to this level, that is x plus y. It has gone from here to here, that is pulley has gone down by a distance x plus y. Stretch in the spring is 2x plus 2y, and this pulley, which has a mass m, has a velocity also, that is kinetic energy also. Now let's use energy conservation method and find the time period of the oscillations. So we say extension of the spring is 2x plus 2y, pulley has mass m, r and ic, and pulley has gone from here to here a distance x plus y, and it has a velocity v. So on the same lines, we say loss in potential energy of pulley is mgx plus y, gain in kinetic energy of pulley is half mv square. Now because when it shall be coming down, it will have a rotational kinetic energy also, that is, it will be rotating also about this axis. Now one thing to note over here is, when this is in equilibrium position, the tension over here and tension over here is going to be the same. It is not going to be different. Because this is in equilibrium position, the torque, this tension which is trying to rotate it this way, and this tension which is trying to rotate this way, and ultimately this is not rotating. If we talk about the net torque about C, that is equal to 0, because this is in equilibrium position. There is no net torque. If there is no net torque, so this tension and this tension, that is going to be same. But over here we cannot say this tension is equal to this tension when it has some acceleration. We cannot say, because this is rotating also, this is going to have some alpha also. So what we do is, we go for the energy conservation method, and over there what we say is that when it goes down, there is loss of potential energy. This loss of potential energy, where it goes? It goes in number one, in increasing the kinetic energy of this mass, and then second is increasing the rotational kinetic energy of this pulley, plus the potential energy of the spring. So the loss of potential energy by this pulley, it has gone to increase the linear kinetic energy, rotational kinetic energy of this, plus potential of the spring. So over here we say that is mgx plus y, loss of potential energy, is equal to gain of kinetic energy of this, plus gain of rotational kinetic energy of this, plus gain of potential energy of this spring. Because there is no slippage between this pulley and this string, so we can safely apply V is equal to r omega, where r is the radius of this. We have done it in rotational mechanics. So omega comes out to be V square upon r square. Now we differentiate this equation with respect to time. So when we say mgx, so this is constant. Why this is constant? Because this is the equilibrium position we have talked about. So x is constant, x is not variable. Derivative of this with respect to time, that is going to be equal to 0. mg dy by dt is going to be v. Then we apply, that is, we get some equation, and once we get this equation, we get it in mg also, in 4kx also, and over here we refer to the equilibrium position. From there 4kx is equal to mg, so this gets cancelled. So this we get, and our expression comes out to be t is equal to 2 pi, that is time period comes out to be like this. So this is how we can find the time period using energy conservation method. Now here we see that this body is rotating also. So can we use the concepts of angular SHM to find the time period? Let's see how we can use that. So if we remember in angular SHM, what we do is when the body is at the mean position, we slightly rotate it by a small angle theta or d theta, and then we look for the restoring torques. Once we get the restoring torque, we say torque is equal to y alpha, and from there we get alpha, that is angular acceleration. And if this angular acceleration comes out of proportion to minus theta, we say this is SHM, and if this is SHM, we use t is equal to 2 pi theta by alpha. This is the same thing what we are going to apply over here. What we do is, now this is equilibrium position, this is a pulley, mass m, radius r, and I about this is IC. Now what we do is, about this point, we slightly rotate the whole thing. So when we rotate it by a small angle theta about this point, as a result, this end, which is at a distance of 2r, this moves by distance s is equal to r theta. We know s is equal to r theta. We know s is equal to r theta. That is length of arc, this is r, this is theta. We know the relation s is equal to r theta, where theta is necessarily in radians. So over here, when we displace it by angle theta, so if this is angle theta, this is diameter, that is 2r. So this point, it slightly moves by a distance 2r into theta. That is 2r into theta. This is a movement of this point. It is so small that it is almost a straight line. So as a result, there is a stretch in this spring. What is a stretch? Stretch is, spring stretches by 2r theta. As a result, the extra restoring force comes out with k into 2r theta, that is k into x. Extension over here is 2r theta. And the whole thing is rotating about this axis only, that is about the point P. So extra restoring torque comes out to be about, this thing is force into this distance. Torque is force into perpendicular distance between line of force and axis rotation. So this is k into 2r theta, force into this distance, 2r. Torque is equal to y into alpha. Now we are talking about extra torque. We shall not be talking about the mg because that had been acting earlier also. So over here we say that is extra restoring force in the spring comes out to be this. Extra restoring torque comes out to be this. Torque is equal to y alpha. So now we say torque is y alpha. Mg will not be considered because mg had been acting earlier also when the equilibrium position had been achieved. So that is used in achieving the equilibrium position. When we displace it from here, we look for the extra restoring torques, right? So this extra restoring torque is this much. Torque is y into alpha. About this if we say, so we have to use parallax theorem, that is about IC plus m into r square. That is ICM plus m into r square. This net torque is equal to I into alpha. From here we get alpha, and once again we get alpha is proportional to minus theta. So this is SHM, t is 2 pi theta by alpha, and we get the absolutely the same time period which we have got using the energy conservation method.